Welcome to a lesson with Dr. Powell. In this video, we're going to talk about what an eigenspace and what an eigenvalue is. So a subspace where the minimal polynomial on that subspace has degree 1, that's called an eigenspace. All right. For instance, if let's start with this matrix right here. Its characteristic polynomial is just the determinant of this guy, right? Which remember what this is. This is just xi minus a, which we're assuming to be the zero matrix, modding out by its columns or its image, its range, saying it's equal to 0. So the determinant of the zero matrix is just 0. So this is going to be a multiple of the minimal polynomial. So the minimal polynomial, the best we can do, x minus 1 and x minus 2, those are potential, those are candidates for being minimal polynomials of subspaces of R3. So factors of this, because they could be factors of the minimal polynomial itself. Okay, so, and anything that's equal to 0, polynomial-wise, is going to be a multiple of the minimal polynomial itself, and so if we get 0 by multiplying by x minus 1, that's because we were in the perhaps because we were in the range of the other part of the minimal polynomial. So if the minimal polynomial was like x minus 1 and x minus 2, maybe we were in the range of x minus 2, so that when we multiply by x minus 1, we'd actually get 0, because that's the only way to get 0. We need to be a multiple of the minimal polynomial itself. And that's actually a very useful idea when we're looking at these things, eigenvalues and eigenspaces, especially if we want to move quickly and with intuition to be able to understand what they are and be able to calculate them without doing a whole lot of work. Okay, so all right, so these are our options for minimal polynomials of degree 1 for certain subspaces, right? We're going to look at the subspace that has that as its minimal polynomial and one that has that. Now, here in this case, we're going to say, well, the x value that makes this 0 is 1, which like a scalar 1, kind of like the identity matrix, that is. But x equals 1, we're going to call an eigenvalue associated with the eigenspace, subspace. We're going to eigenspace where the minimal polynomial is that guy. Okay, and x equals 2 is going to be the eigenvalue for the subspace where this guy is the minimal polynomial. Now, what does that mean, really? I mean, for like this guy to be equal to 0 in that subspace, that means if you throw a vector into this matrix, because this is a matrix, if you had like 2 times the identity, think about, or even their actions. If you throw a vector into that, let's just think about what that means. And then thinking about how addition works with functions or matrices or whatever else, you could actually distribute this v in. So you could think like x times v minus 2 times v is equal to 0. In other words, x times v is equal to 2v. Wait a minute. So if v is in this eigenspace, that means x acts the same thing as the way the scalar 2 does. That's going to be very useful for us. So we're looking at subspaces where x actually acts like a scalar. And what scalar does it act like? Well, in this subspace, it's going to act like the scalar 2. In this subspace, it's going to act like the scalar 1. Just multiplying by 1, multiplying by 2 is going to be the same thing that the matrix X does if we're in this subspace versus this one. Okay, so we're going to take a look and try to figure out what those subspaces are, what those eigenspaces are. We know what the eigenvalues are just by looking at this and calculating the determinant. Even though we don't know the minimal polynomial, we do know that it is a factor of this characteristic polynomial. Okay, so let's keep going. Each factor of the minimal polynomial, whatever it is, it's either this guy or this guy, holds dimensions. Now, why do we know it's this and this? I mean, don't we just know it's just a factor of this? Well, the minimal polynomial itself, I mean, if we found that diagonal matrix, remember that, or even the Smith normal form, if you will, in a modular sense, or polynomials, and we're looking at that. The least common multiple of the diagonal was the minimal polynomial overall. And actually, if we're just using airdropping the whole time in our calculations, so to keep things minimal, the product of the diagonal is the determinant, and the only things that we really see in the product are these polynomial factors of the minimal polynomial itself. At least so really the x minus 2 is going to be in the minimal polynomial, and x minus 1 is as well. So we can actually get a lot of information from the characteristic polynomial. So we know that this is the minimal polynomial, or this guy. It's one of the two. But it's helpful to realize that each factor holds dimensions as we do this. We can actually decide which of the, it's a multiple choice, like which one is the minimal polynomial. We can decide this by just running a quick calculation. So we don't even have to do any row or column or any column operations on polynomial column operations on this guy. We don't have to do any at all. All right. We can just, we can, if we think about what's going on. All right. So, all right. So in this particular case, if this was the minimal polynomial, that meant that since we have to get a determinant that looks like this guy right here, that means that x minus 1 must be a factor of two different diagonal entries, especially if we're finding a least common multiple. Okay, in that case. So that would mean that x minus 1 itself is a minimal polynomial in like two different dimensions, two different places. So like x minus 1 would hold two dimensions within it. So it would only have one dimension left to get to 0, which would be taken on by the x minus 2. You could kind of think of it that way loosely, intuitively. So we can, if we just look at the matrix x minus 1, which is pretty simple to compute, you just take the matrix and you subtract 1 down the diagonal. If you look at that and you look at the columns, and if it looks like the columns are all multiples of each other, it's one-dimensional, that would mean that this is actually the minimal polynomial in that case. All right. So so it's making x minus 1 itself is making two dimensions go to 0, being a minimal polynomial in two different places. This case right here can only happen if x minus 1 squared is a factor of one of the diagonal entries itself. And in particular, the range of x minus 1 x minus 1, if you just multiply it by it once, it would only maybe cause one dimension to go to 0, namely the range of x minus 1 itself could, it's actually the range of x minus 1, x minus 2, right? So that guy, it's not 0, so it has to have some kind of dimension, and x minus 1 multiplied to it would cause it to go to 0 minimally in that case. So, so each time we multiply by x minus 1, maybe we'd only be going down. Okay, we'd only be going, so we wouldn't be, so taking a look at that, maybe it would be two-dimensional, because we still have to multiply by two different linear factors to get down to the minimal polynomial. I mean, this is just kind of intuitive at this sense, but is great for calculation's sake. Okay, so let's take a look and go forward. Let's look at x minus 1. Notice that it has a one-dimensional range. Okay, these are multiples of each other, which means the minimal polynomial really is x minus 1 times x minus 2. So you're not going to have any entry in the diagonal that's going to have x minus 1 squared. By the way, just for future reference, if you're trying to diagonalize a matrix by using this, what does that mean? Well, later on we'll have some videos that explain it. But you're trying to like multiply a matrix on one side by a matrix, by another matrix, and the other side by its inverse to get a diagonal matrix. That's actually only possible if you don't have any squares in your minimal polynomial, so you don't just have things like this. So in that case, when it is diagonalizable, we can always assume that these guys are always like that, and that's actually really useful if it is. Okay, so if we take x minus 1, That's just the original matrix here, and we subtracted 1 down the diagonal here. We get this, and these are one-dimensional range. That's the minimal polynomial. So let's actually go ahead and try to compute our eigenspaces. All right, a lot of commentary, but that's for understanding purposes here in this example. So if we take the range of x minus 1, okay, so looking at x minus 1, the range of x minus 1, if you multiply it by x minus 2, you'll get 0, because that's the minimal polynomial right there. So we just take a look at that, and so it looks like that's the eigenspace for x equals 2, right? Because this right here is the range of that, and so if you multiply it by x minus 2, then you'll get 0. So, and you can even try it out. If you plug this right here into this matrix function here, does it just double it? Let's see if it does. Does it just double that vector? Then this would be the eigenvector. That would be the eigenvalue. Let's see if it does. So if we plug in 2, 1, 0, see what this means. This means double that column and then add that column. So that would give you 4, 2. Yes, it doubled it. Hooray. Okay, so that is our eigenspace right there with an eigenvalue of 2. All right. So now let's take a look. How do we compute the eigenspace at 1? What do we do? Well, we find the range of x minus 2. Okay, so we find the range of x minus 2. So we look at x minus 2, we subtract 1 down the diagonals from x, you get this. Notice it's pretty clear to see what a basis is for the columns. Now, if it's not clear to see what the basis of the columns is, you can always resort to trying to put it in reduced row echelon form, then looking at pivots and going back and seeing what works. And that's always an option. But sometimes it goes pretty fast just looking at it in this case. So here, notice that you have 1, 0, 0 and -4, -2, -1. That is a basis for the range of x minus 2. And anything in the range of x minus 2, multiply by x minus 1. Let's see. Yeah, multiply it by x minus 1, and it'll be 0. That's like the matrix is acting like the identity on it. It returns itself. It just multiplies 1 to it. So let's take a look at that and see if that is actually what happens when we throw these into the matrix here. So if we put in 2 basis vectors, 1, 0, 0, what happens? Pick out the first column. Hey, yes, it did nothing to it. It acted like the identity. Now let's try the other one. -4, -2, and -1. So -4, -2, and -1. All right. And we'll write that -1 like this. All right. So put this in. So we could think of a row interpretation if we want to, which means we basically say 1 times that row plus 2 times that row plus that, and then just put it there. That's fairly simple, or just taking dot products really. So there's different ways of doing matrix multiplication, but anyways, -4 minus 4 and plus 4 would give you -8 plus 4, which is -4. Amazing, it worked. Okay, in this case, dot product of -4 and +2. Hey, that's -2. Okay, here just -1 times that is -1. It worked. Okay, so we get 2 eigenspaces associated with eigenvalues. One has dimension 2, one has dimension 1, and we have the bases of them. And all we had to do was just look at the ranges of these guys, knowing what the minimal polynomial was, enabled us to do that. And how did we know that was the minimal polynomial? That's because x minus 1 itself had a one-dimensional range, meaning that it sent 2 dimensions to 0. So you take so x minus 1 sent 2 things to 0, which meant that x minus 1 occurred like x minus 1 itself occurred in two different locations. If x minus 1 occurred in one location, then it would only have been affecting one dimension. The number of for that particular linear factor. So linear factors, the number of times they actually occur is equal to the number of dimensions they send to 0. So the complement of that is 1, and that's what we will want it to be, what was actually still there in existence there, one-dimensional range. And so we knew that this would be to the first power, since we knew the characteristic polynomial, the determinant, was x minus 1 squared. But so there were two things in there, but it didn't happen all in one spot. It happened in two places. All right, so that was a little description of what eigenspaces were and what eigenvalues are in terms of minimal polynomials. Thanks for watching.